Okay, good morning. So let us take an example. A phase a three-phase star connected 220 volt. This is line to line to line voltage, 60 hertz. 60 hertz is a US supply system. The machine is taken from, data is taken from that system. 6 pole. Okay. 6 pole machine has the following parameters. The parameters are as the following constants. As the following constants in ohms. In ohms per phase with respect to the stator. With respect to the stator, R1 stator resistance, R1 is equal to 0.294. Okay, R2 is equal to 0.144. Right? Okay. Then X1 is stator leakage inductance is equal to 0.503, and X2 is equal to, X2 is the rotor side leakage. This can be taken as R2 dash and X2 dash is equal to 0.209, and XM is the magnetizing reactance. XM is equal to 13.25. Right. So this point. Right. So what is the way done is that first of all, our analysis and our understanding of the machine from the drives perspective, we have said that okay, so the thing is that let us say that the slip is 2%. Slip S is equal to 2%. 2%. Let us see from our understanding at slip is equal to 2%, what will be the torque. Let us find out what will be the torque at slip is equal to 2%. And in this, in the last class we have also mentioned that in this we normally consider a simpler equivalent circuit where all other parameters will be negligible compared to R2 dash by S, which we can cross check, because here you see that R2 dash by S is how much? It is equal to 0.144 divided by 0.02, right? So that is equal to the number is then that is number is equal to R2 dash is where did I write? Let me use the calculator then.
7.2, sir.
Yeah, that is 0.144 divided by 0.02. right? That is equal to 7.2, correct. So 7.2 ohms. So you see 7.2 ohms is much larger than the comparative value of R1, X1, X2 dash, and don't compare with XM because XM is a shunt branch. So it doesn't matter. So it doesn't matter. XM can be anything. It doesn't matter. It matters as far as the current is concerned, but doesn't matter as far as the torque is concerned because our equivalent circuit is in the equivalent circuit. You can remember that I have taken a voltage and a resistance. That is the equivalent circuit I have done. And this thing being parallel doesn't matter the current that is there in I2 dash part. And while torque, finding out the torque, we are taking only this part. So this is R2 dash by S and this is the V, right? So how do we solve this problem? First we write the torque expression that we had written earlier. So TD is equal to what? That is, you see how I am writing voltage by fluxes square. I will write it in that form. So voltage is how much? This is 220 volt is the line to line voltage. So 220 divided by root 3. What is the divided by omega sin? How much is the omega sin? Synchronous speed. How much is it? Can you tell me? How much is the synchronous speed?
1200 RPM.
No, 1200 RPM. It's good. You have understood that it is 1200 RPM corresponds to 1200 RPM. How is it coming? It is coming because it is a 60 Hz machine into 60 divided by number of pole pairs. That is 6 by 2. So 60 Hz machine, 60 is the in the minute, since it is not seconds but in minutes, RPM, revolution per minute, and that corresponds divided by the poles. So it is this. So I will write in the omega, I have to give the dimension properly. I have to write 2 pi into, I will not use this thing in the RPM in this form. This is 2 pi into Fs. So this is equal to 60 by 3. That means 20. 60 by 3 is 20. That is what is the value of this. So this square, right? Into 1 by R2 dash. R2 dash is how much? R2 dash is equal to 0.144, right? Into omega S omega sin. That is the term. That is the term is there here into this. Why 3? Because it is a 3-phase. Okay, last time I have not used 3 because I was considering per phase, but when I want to know the total torque of the machine, I should use the number of phases. So this is the expression of the torque, right? So now in this case, if I put the numbers, in fact I should have put S omega sin also. So but I want to show you separately this part. S omega sin is equal to how much? S is equal to 0.02, right? 0.02 into omega sin. Omega sin is equal to 2 pi into, my pen is giving problem, 2 pi into 20. So this is equal to how much? S omega sin in this case, let me calculate. 0.02 into 2 into shift pi into 20. So that is equal to 2.513. Please check if I am making any mistake. So now what is the torque? If I do the calculation, what is the torque? Let me do it again. 220 divided by root over of 3 divided by 2 divided by shift pi divided by 20. That is the term. So I am just separately, in order to that we get a number. 1 point, I am trying to show you the numbers. 1.01 is this number, this is square, okay, into S omega sin is equal to 2.513 divided by 0.144, right, into 3, right? So it is coming out to be 52. Torque TD is coming out to be 52.918 Newton meter, right? 918 Newton meter. If this machine, suppose I ask a question, if this machine has to develop a torque of this, let us say TD, now new torque, TD1, another torque. suppose it has to develop a new torque of 30 Newton meter. Suppose this machine has to develop a 30 Newton meter, and I have not, let us say, I want to know that how much it would be S omega sin. Here the S omega sin is how much? This is 2.513. How much will be the S omega sin now if I want to generate 30 Newton meter? As per our understanding, the new S omega sin combined omega sin, that is the new for 30 corresponding to 30, that product has to be, it doesn't matter what is the numerical value of omega sin. What matters is the product term, because the torque expression has been written in this way. And this part is never changing. This divided by omega sin, this V by omega sin, this part, this red part will never change. Even if you change omega sin, because you will correspondingly change the voltage. This part will remain constant. This part will always, for this machine, it represents the flux. Flux is square, in fact, the flux. So flux is not never changed. So this part is never changing. So the changeable part is only this fellow. Changeable part is only this fellow. So what will be the S omega sin now? You can see that it's a linear equation. It is proportional. So it will be something like 30 divided by 52.918 into 2.513. Right? How much is it? 30 into 2.513 divided by 52.918. Right. So it is coming out to be 1.4246 in radian per second. These are all numbers are in radian per second. Radian per second. This is a number corresponding to a radian per second. Okay. This radian per second corresponds to how much RPM? This radian per second corresponds to how much RPM? Let us see how much RPM. 2.513 divided by 2 divided by pi into 60. So that is equal to 23.33 RPM. Is that correct? Is that correct? This is equal to a corresponding to 24 RPM. Let us cross check. Yes, it is true, because it is 1200 into 0.02. So that is 24 RPM. So this radian corresponds to 24 RPM. This will correspond to what RPM? This will correspond to 1.4246 into 60 divided by 2 divided by pi. So this will correspond to 13.66 RPM. This gives us a physical thing. That's why I'm writing in RPM. While doing calculations, we should use radian per second because that is the omega's proper dimension. But in our normal understanding, we always use this kind of RPM. So what does it mean? What is it meaning? Let us try to understand this meaning in terms of one chart that I will do now. Right. The chart is somewhat like this. I write in one corner that my condition is that rotor speed that is demanded. Rotor speed, right? That would be demanded. And what else would be demanded from the process? The process will also demand the torque, which most of the time I don't know. Torque. Rotor speed at least is a command given to the machine system, the machine drive system. The process control system will give this command to the drive system that please run the motor at such and such speed. That command is given. Only that command. But after that, it implies that you should run at that speed irrespective of the torque demand on the motor. Okay. So that will be, again, that means suppose a conveyor belt is there. So they only tell you that conveyor belt should be run at some 10 meters per minute. which may correspond to a rotational speed of, let us say, 600 rpm, such and so and so. So they will give you this 600 rpm information, but they will not tell you that conveyor belt is loaded by how much weight it is carrying. That they won't tell you. That the machine system is supposed to develop the adequate amount of torque, okay, and still maintain the speed. The torque on the conveyor belt may vary without any information to the drive system. Drive system is only getting the information of the demand. The demand is like you run the shaft or the machine at 600 rpm. That kind of demand is coming to it, but it has to adjust. But the torque is existing. So torque is an unknown input, but it is an input. At the moment, we are back calculating. We are saying that, well, if the torque demand is this much, I will take such and such action. I will take what action? I can take only one action. That is, I can decide what should be the synchronous speed. The difference between rotor speed and synchronous speed is the difference of S omega S. So I am deciding S omega S because I know S omega S is proportional to the torque demand. More torque demand, more S omega S I have to develop. So accordingly, I will do what? I will decide the synchronous speed, because that is what is the speed with which the supply will be given. Not 100% true, supply will be given synchronous speed into P/2. That is the electrical frequency that will be given. But first you should know synchronous speed in order to know the supply frequency. Electrical supply, that 50 hertz, 60 hertz, or 10 hertz, or 20 hertz, that you decide. Because you are in the drive system, you have the ability to decide this frequency, supply frequency. But you also know that in order to maintain the flux level constant of the machine, you should not just change the frequency, you should simultaneously change the supply voltage magnitude. So that V by F ratio, you must V by omega, V by F. This omega or F is the supply things frequency. Okay, so that you have to maintain. So torque demand at this moment as if we know, right? But in reality we will not know. So then we will show you how to do that. Then we will say based on that we should know what should be the S omega S. Then what should be the omega S? I will write all in RPM for my convenience. You understand what I mean. Actual thing is easily convertible to the proper radian per second. I am just writing in the sense that we normally understand. And then I should decide what should be the stator voltage. I am writing S. Vs means stator voltage. Stator voltage. For the machine for which I have taken such an example. So rotor speed, let us say I am arbitrarily choosing. Say this, they have said that you run the rotor, you let the rotor speed be 400. Rotor speed is an RPM, let us say. They have asked us to run the machine at 400 RPM. And if the torque demand would have been how much? Let us take the first one, that is 53, about 53 Newton meter. About 53 Newton meter. How much we had calculated? It was, how much it was? 52% slip. How much it was? It was 53 Newton meter, roughly 53 Newton meter. So if the torque is now 53 Newton meter, okay, the demand is like that. So then we'll get a slip of 2%, and S omega S of 1200 is the and I don't know what is, I only know that it has to be 24 RPM, 24 RPM, because we have calculated that S omega S becomes 24 RPM. That is unchanged. So omega S will be, that means the supply frequency has to be, supply frequency here I am writing in the mechanical way, but so understand it what I mean, 424 RPM, right? Actual frequency will be how much? Actual frequency, let us say you are right also Fs, right? So actual frequency will be 424, right, into divided by 60, okay, into this is RPM, so revolution per minute. So yeah, 2 pi f into 2 into I'm getting confused. 2 pi f is equal to omega. So omega by 60 is equal to divided by 2 divided by pi. Yeah, divided by 2 divided by pi. Yeah, right. So how much is it? 424. Okay, into number of pole pairs into 3. Right. I should not forget that 3 is the number of pole pairs. So 424 into 3 divided by 2 divided by pi divided by 60. So how much it is? What is the mistake I made? 1200 RPM. I should divide it by 60. Okay, 20. Oh, sorry, this 2 pi is not coming. 2 pi is not there. I am talking the frequency in hertz. So 424 divided by 60 into 3. So it is 21.2. It is 21.2 hertz. That is the frequency with which you should give. And what will be the voltage? The voltage will be for 400 will be what? If this were 1200, that is will be 400 and 220 is the line to line voltage. Let me put it in 220. I'm talking line to line. Let me clarify here. This is line to line. That is 220 is the original one, right? And now the frequency that is corresponding to 60 hertz. So 60, and now we are running it at 21.2 hertz. So it will be into 21.2. This 402, this corresponds to this is the RPM, right? So how much is it? 220 into 21.2 divided by 60. So it is 77.7 volts. 0.7 volts. Right. Right. Have you understood what I say? Has anybody has any question? The chart I have filled up. If the rotor speed is 400 RPM, it's the demand, and that time torque is 53 Newton meter. The S omega S must be 24 RPM. So the supply, the synchronous speed should be 424 RPM. The 424 RPM will boil down to a supply frequency of 21.2 hertz. It is nothing but 424 divided by 60 into the number of pole pairs. And since it is running at 21.2 hertz, the line to line voltage that you need to produce under such situation is scaled by the original frequency of 60 hertz. This 60 is corresponding to 60 hertz. So 220 by 60 into 21.2. So that our V by F ratio remains unchanged. Original V by ratio is 220 by 60. That is the V by F ratio. V I have taken line to line. If you want to take phase wise, just 220 divided by root 3. So that is not a big deal. The ratio wise, if I consider line to line all the time, then I can take 220 as the voltage for the V by F ratio. 220 by 60. 60 is the supply frequency, original supply frequency of the machine, right? So when the machine I am operating at as a variable speed operation, this is what I am supposed to do. I am supposed to generate a voltage, sinusoidal voltage of 77.7 volt RMS at the motor line to line terminals, and the frequency of that should be 21.2 hertz. Then I am expected to, in a Bragg, I am expected to get a rotor speed of 400 RPM and the torque will be 53 Newton meter developed by the machine. Yeah, some question is coming. Anybody? Hello? Is there anything you want to ask? Right. So And just to make it one more time, this point little more clear. Suppose you want to now develop 400 RPM, but 30 Newton meter torque. Then what should be done? 30 Newton meter torque, we have calculated that it requires some about 13 RPM extra, 13.6 RPM extra. S omega s, 13.6 RPM, right? This is what is required. So what it would be? 413.6 would be the omega s. So what it would be? 413.6 divided by 60 into 3. That will be the frequency. So that would be how much? 413.6 divided by 60 into 3. So that will be the frequency. That will be how much? 20.668, 20.7 approximately. 20.7 hertz will be the frequency. Okay, what will be the voltage? Voltage is 220 into 20.7 divided by 60. So how much is the voltage? This is the voltage. 220 into 20.7 divided by 60. So how much? 75.9 volt. Right. So this is what will happen. If now somebody wants to run the machine at 600 RPM, but still produce 30 Newton meter, then what it will be? It will be 613.6 Newton meter. Here it will be how much? 613.6 Newton meter, 6 RPM. RPM, this is not Newton meter, RPM. Okay, this is RPM, and you can now calculate this one and this one as well, because you are always having the V by F ratio constant. So you know 616 RPM will corresponds to what? 613.6 divided by 60 into 3, right? It is 30.68 hertz. 30.68 hertz, right? And the voltage will be 220 into 30.68 divided by 60. So it will be 124.5, 112.5, 12.5. So this is the way you should do it. You take any speed. This is the method. This is where the machine has to ultimately land up to. This is if I need to give this kind of voltages to the terminals, and the machine will eventually respond by reaching a steady state speed of rotor speed of 600 RPM and developing a 60 Newton meter torque at the shaft, which the load demands. Okay, this is the way the equilibrium will be established, because the machine will be developing the same torque as the load torque. So there is no further acceleration or deceleration. Till it happens, machine will be either accelerating and decelerating, and there will be a search for the right amount of S omega s. This S omega s has to be searched by a closed loop control system. That is what will be the method involved. Okay, so this is what I wanted to clarify, that the entire control is based on ideally finding out first the right amount of S omega value, S omega sin value, and then correspondingly choosing a voltage magnitude at the terminal. If you do any kind of induction machine control, this is what will be the essential objective. There are various ways of arriving at it. Some people call it vector control, some people call it direct torque control, but none of them will violate it. Okay, the simplest possible way of achieving it is called the V by F control, right? Now you obviously understand that here, in order to determine the right amount of S omega sin, we need the torque information, which is not available externally, which is not available to the drive system. So drive has to do what? It has to do a search method, a kind of trial and error method. Trial and error method means what? It will, let us say, arbitrarily choose 15 RPM. Suppose in this case, it will first choose 15 RPM. So then it will go to a higher, it will develop a higher torque. So machine will accelerate. The speed will go higher than 600. Then the error will be developed because the reference is 600 RPM. That is what is demanded. So the control system will develop an error, and that error will be then producing lower synchronous speed. We'll have to give a lower synchronous speed, and then that will be tried. And this way, the error will have to be brought down to 0, right? This is what you have learned in your course, like control system, like a P proportional integral controller. Integral controller does what? Integral controller makes sure that the value of the error under steady state is 0. Why it is 0? Because the integrator is there. So integrator, if it is not 0, the moment till it is not 0, there will be an output correction amount, or in this case the correction amount is the synchronous speed. It's not the synchronous speed, it is synchronous speed, but essentially it is s omega speed, sleep speed. We call it sleep speed, or sometimes we use it a name, give it a name. Sleep speed we give s omega s. So till the sleep speed amount is sorry, still the error in the speed is 0. Error in the speed means speed reference minus actual speed is 0. The sleep speed will continue to vary through an integrator. Let us take proportional part out. First think about an integrator, because error is then integrate, it is trying, and the moment it is trying, it is going in the direction of reversing the error. Okay, it should be such that its intention is to reduce the error, right? So this way it will go increase, decrease, and finally it will. That's what you see the oscillations in this. That is what is the controller is trying by trial and error. It is trying, and ultimately it is arriving at the correct amount of sleep. Correct amount of sleep that would be required in the system. Okay. See, this correct amount of sleep as calculated by this method and the real life sleep will be maybe slightly different, because we have assumed the resistance to be just that. But suppose the temperature of the machine has increased, the resistance has slightly varied. Then in our case, we will not be able to arrive at the correct amount of torque, because we have assumed that the resistance to be constant. But in the closed loop method, it is already included, because it is directly working on the speed error. And for that particular time, whatever may be the parameter of the machine, taking consideration of the temperature, saturation, etc., all other things, it will develop the precise amount of slip speed that will ultimately develop the torque, as well as maintain the control or regulate the speed at the reference value, the rotor speed at the reference value. So let me draw the control system now. Right. So let me draw the control system of this scheme.
Sir?
Yeah.
Sir, so we are able to know the slip speed because we know what the torque is, like in this situation when we are calculating. But in real life, like how is torque like measured then? Like what is the real life system?
Torque won't be measured, but you understand one thing. Let us look at this way. If this torque, do you understand that this torque is developed by the machine, right? And this torque is demanded by the load, right? Let us say you are saying 30 Newton meter is at that time the torque in the load, right? And we are supposed to develop a torque that is precisely 30 Newton meter under steady state. Okay. So in between, if you have failed to do so because you don't know correctly the signal, you are trying, you are pretty much guessing. You say that let me try with a speed of, with a slip speed of, let us say, instead of 13 point something, let us say we tried with 16. Okay, so what it will do, if I try with 16 as the slip speed, what it will do? It will definitely produce a more torque than 30 Newton meter, because precisely 13.6 RPM slip speed would have produced 30 Newton meter. But now we are producing from the machine more than 30. Let us say we have produced 33 Newton meter. So what is the consequence of that? Then J d omega dt is positive. So therefore, what is happening? The rotor speed will be, this omega is rotor. Rotor speed will be increasing. And what is the implication of rotor speed increasing? Implication of rotor speed increasing is slip decreasing. So you see that it is going in the correct direction. That's why we have chosen this slope. That's why we have chosen this slope to operate on. Okay, so it will be, then you will see that the error is reducing. So that means you will see that the corresponding adjustment of the slip speed will reduce, because you have known that you have gone in the wrong direction. You have overshoot the demand. You have produced more torque than the thing. That's why the rotor speed has increased. I will draw the closed loop and you will understand. It is not required to measure the torque. That is what the beauty of the closed loop system is. That is what you should appreciate. Maybe I should show you a little slowly, but you will appreciate it. You will appreciate it. Let me do it in here. These are all summer block. This is all summer, SUMMER, summation block. I will show you what only speed feedback is required. This is a TACO. TACO is a thing which you have not machine lab, whether you have done or not, I don't know. You might have seen in the machine lab, which is used to measure the speed. This is the machine. And this machine is coupled to a shaft. This is the load. Okay, I should put the TACO on the shaft. Let me little bit correct it. TACO is connected to the shaft, which is giving you speed feedback. That means you know the actual machine's speed. Okay, now how the machine will get supply? It will get supply like this. It's a 3-phase machine. Okay, 3-phase supply. How is it getting a supply? It is getting supply from a converter, power converter. This power converter in our term is called inverter. Why we need inverter? Because we need to produce a variable voltage, variable frequency supply. Inverter will be producing a variable voltage, variable frequency supply, because the supply system, original supply system is frozen in frequency and the magnitude of the voltage. But in this control, when we require the speed control of the machine, we need to produce a variable voltage, variable frequency supply at the terminals of the machine, induction machine. Okay, so this is the machine, this is the inverter, right? And then this is, so since in order to produce this intermediately, we need a DC voltage. So this is a DC voltage that has been produced. How did you produce a DC voltage? For the time being, we understand that it is produced through a rectifier. Okay, and then where is the rectifier supply? It is a 3-phase utility supply. This is the utility supply. Utility, you understand, the 3-phase utility supply, 3-phase. That means in our system, in our Indian system, it is normally 415 volt, 50 hertz supply. Here 415 volt implies line to line voltage. Must understand that convention is always to speak on line to line. So you that 415 volt 50 hertz supply you have rectified. rectifier, and you have produced a DC plus minus a DC, reasonable high value, maybe about 600 volt, about 600 volt DC you have produced. Okay, for the timing taken simpler number 600 volt, it may be 567 or 580, but let us consider that to be 600. Okay, then we have a power converter. We will come to that, what power converter. But see the objective class. Objective is to produce Vs omega S. Okay, okay, at variable. Omega is S is the supply frequency. Vs is the supply voltage, who are variable. Okay, so this option I must have. Now, how do I link? These inverters are essentially semiconductor switches. So I need only things 6. There are gate pulses. We call it gate pulses. It may be consisting of IGBT. It may be consisting of MOSFET. What is qualitatively known is the gate pulses. So that means gate pulse is a switching signal, which says you turn on now, you turn off now, turn on now, turn off now. We can do only this thing here, right? So only this thing is required from the control system to this. Okay, I will come to that. So here it is gate pulse. It generates gate signals. Okay, my pen is creating problem. Anyway, gate signals. Gate signals. Gate to the semiconductor devices. And you require normally inverter, 3-phase inverter. You have 6 devices. So 6 pulses will be giving. Okay. Now what happens? Let us say, now again come to the control part. This is the power part. This is what we conventionally considered as power circuit. Power circuit. This is what is power. The actual torque production, actual energy transfer, they are happening here. But this is other part is a control part. Control part means it is a code. It is a code with instrumentation, with some instruments giving you signals. They are not power. They are all signals in millivoltage level. Millivoltage level in analog domain, and in the code domain, it is just a code. After analog to digital converter, you have taken all the analog signals. This is a measurement unit. This is a measurement tacho. Tacho is a speed measurement unit. TACHO, tacho generator is a speed measurement. Tacho generator has given some voltage signal. Through some ADC, you have put that into your computer. It can be a microcontroller. In the microcontroller, because this signal, I am not writing it through a analog to digital converter. The analog signal will be converted to digital, and then it is in the digital domain. This is in the control domain. Okay, so where the signals have no strength and their voltage levels don't matter. Okay, you may understand in digital level everything is a code, right? And the codes are means only operating on digital logic of high and low. So a PI controller is also written in digital domain. It can be written. It's a code. Okay, integration can be written in terms of a code. Multiplication can be written in terms of a code, right? So let us not bother too much about whether it's an analog and digital thing. You should understand this is in the control domain. Meaning, feeling wise, there is no high voltage. There is no way of dying because of that. But in the other part, power part, you may die also because the voltage levels are so high. So here it is nice and clean in a computer or in a simple op-amp circuit. This way you are constructing this part. And eventually what you are doing, the construction level is only converted into some high and low signals, which are gate signals, finally, eventually. So the gate signals with which it goes to the, through a gate driver thing, it goes to the inverter semiconductor. That is where again it is interfacing with the high voltage part. The gate signals through gate driver again it interfaces to the power part. Okay, that is the link. The link is a gate driver. The controller is generating a gate signals, that is digital signals, high or low. From that you are generating a much high powered signals that would be required for the semiconductor devices. Okay. So I hope I am going to get you are getting the this thing. So here you give omega rotor reference. Please understand very clearly. This is what is given by the process. Process will give you process, but it will not give you what is the torque. So what you are doing, you are doing this way. You are taking the feedback. So you are seeing the rotor, actual rotor speed. This is omega rotor. This is the actual rotor speed, and you are doing plus here, minus here. That means you are developing, knowing whether there is an error between these two. Now you have seen that if there is an error and the error is positive, suppose the error is positive, what does positive error mean? Positive error means that omega rotor reference is greater than omega rotor. That is what it is meaning. And what does it mean? Your action should be such that the rotor speed catches up, rotor speed increases and tries to match the reference. That is what your intention is at a certain instant. I'm saying you should not assume that all the time these two are matching. No, that is what it is taking care of. That if it doesn't match, what happens? What do? We take a corrective action. What corrective action we are taking? Based on the positive error. If the error is here positive, let us say positive, then PI control, even if it is an integrator positive means what will happen? It will increase. It is integration of some say, let us say, integrate your positive thing. Positive thing means what? It is continuing to increase here. So if it is continuing to increase here, this is what we are determining as slip speed, S omega sin value. This is this is what is S omega sin value. This is what we are treating as correction amount, the synchronous speed, the slip speed correction that we need, which we are adding with rotor speed to generate the actual synchronous speed. And actual synchronous speed, when we know, then we are determining what should be. There is a curve like this, from which V by F curve, we know what should be the voltage, stator voltage. What should be the stator voltage amount? In control sense, these are signal levels. You must understand that. It has not yet been, it is not related to it is a kind of proportional thing, but much lower voltage thing of the actual physical system. So this is the voltage we are getting, and this omega and V sin, this information is then going through a thing called modulator. I will teach that later. Modulator, and that generates the gate signals, high and low signals. Modulator's job is to get these two informations, this omega sin and V. These two information it should get, and correspondingly generate the gate signals. Correspondingly get the gate signals, and that will be given to the inverter. Okay, so now you ask your question, what is that is you are not understanding? So since it is increasing, the correspondingly omega sin is increasing, and if the omega synchronous thing increases, then it increases the torque, and if the torque increases, then the speed increases. Then what is happening? Actual speed is increasing. Therefore, actual speed is catching up, and the error is reducing. And then the error is reducing. Then means PI controller is now integrating with a lower slope. Okay, it may even be increased so much that it may go to the negative slope. So by this increasing or decreasing, it is arriving at the correct amount of slip speed. Because that action is there. The integrator is doing this thing. Have I answered you or not? Even if some small doubt is there, you may ask.
Yes, sir, I understood.
This is done by the integrator. And the integrator is placed in such a way that in case I have made a mistake in knowing the correct amount of slip speed, the action will be such that means if I have made a mistake in knowing the correct amount of slip speed, it will either produce more torque or less torque. More torque, okay, if I have given somehow given more synchronous speed, right? So then what will happen? Then the machine will accelerate, and the moment machine accelerates, you know, its slip is reducing. Isn't it? If the machine accelerates, then what happens? Its slip is becoming less. And when the slip becomes less, torque becomes less. And the torque becomes less means it doesn't accelerate that much, or it will stop to accelerate. And eventually it may even decelerate, right? If you have overshot, then you may decelerate. this acceleration, deceleration, acceleration, deceleration will continue, and eventually it will reach the correct speed. Okay, for any amount of torque, it will be reaching the correct speed. The speed may be going like this, and through a oscillation will reach the correct thing. Because at that point you have got the correct amount of slip speed that would be required to run the machine at the correct torque. Before that, here you see that this is reference speed. This is reference. This is omega rotor ref. This is this value. The actual omega is this. This is time, right? This is time. So in this portion, you see that the rotor speed had increased more than the reference speed. Okay. So then what it means that then omega sin was negative, and when it was negative, it was producing torque in the other direction. So therefore, the speed had to reduce. Okay. The speed will be then reducing, and this thing will be continuing till it is still continuing to try, and eventually it reaches the correct amount of speed. Okay, why it has reached the correct speed? Because it has calculated the slip speed now correctly, and this correction is this calculation which we are numerically doing is done by an integrator. Integrator's beauty is that it can only stay inactive if the error becomes 0. Then only it will maintain the slip speed to a constant value. Otherwise, if there is a plus, it changes. If there is a minus, it changes. And that's what we want. Plus and minus is implying that there is a difference between the reference speed and the rotor speed. And that is what is the first demand, that you run this thing at the desired RPM. Why it might not run? It might not run because your torque development was not correct. And why your torque development was not correct? Because you didn't get the correct amount of slip frequency. And so what do you do when you don't get? You produce an error that will be reflected into an error, and the error will be making sure that you go in the right direction. Right direction means if your torque production is less, you will increase the slip speed. If the torque production is more, you will reduce the slip speed. That right direction, and that reflects into the rotor speed. So by measurement of the rotor speed and by putting a PI controller, we can correctly predict, we can correctly arrive at the value of the right amount of slip speed. That is why it becomes a closed loop control system. It is a closed loop way of doing this. You don't have to do anything. It takes care of all the non-areas. It takes care of some variation in the motor resistance and some other aspects of it, a little bit of saturation, etc., etc. Because it is catching it on the fundamental level. The fundamental level is that it is supposed to maintain the speed, and the error in the speed will result in the correction. This is the error, this is error, this side is error, and it is correction. This is resulting in correction, and it is in the correct direction. If the error is positive, I must increase the slip speed. Error positive is meaning that more torque demand is required. More torque is required than what it is at that moment. So it will increase that. So this is the way this system will work. Understood it? Okay. Understood the control system? So this is the synchronous speed. This is the characteristics which is, I said now V by F is constant. That means what? If I give synchronous speed, it will correctly give me this characteristics is like this. V by F character, this block is like this. This block, I'm blowing it up. This is the characteristics. Ideally, it should be a straight line. Straight line means this is omega sin and this is corresponding Vs. So for every V in, I will know supply voltage. Though in reality, we may learn a little later, the characteristic curve is slightly different. It is slightly, a little bit of DC shift is given. Then you match it here. It is like that in reality. But for the timing, you understand that V by F is equal to constant. The essential is V by omega sin, Vs by omega sin is equal to constant. So this will dictate what voltage we need to generate. And then when we know what voltage and what frequency we need to generate at the motor terminal, we have to generate the appropriate gating signals, that when I switch should turn on this switch or that switch. And that is done by a thing called modulator. That is what I am saying, that is called modulator. So you know that now our study will be concentrating on, from next class, what is an inverter and what is a modulator. These two are things to learn. Control system part will leave aside. Control system will assume that it has been properly designed. Though if it is not properly designed, you will see speed is hunting. Speed is never coming to the reference value. It is going high and high, low and going high and going low. It is continuously hunting. Okay, this is called instability. So you will see that. But we say that this is a different subject where you need to know the system's poles and zeros. You have to write differential equations, which probably you have learned how to do it for a system, and then find out the system transfer function, and then you can design a PI control. This is HS. The rest of the thing is, what you call GS, system transfer function. And the PI controller is what in the control system you have learned as HS. So given a GS, we should be able to find out a PI control. That skill, I am assuming that you have learned, or you have at least got an idea that what method I must use to do that. So thinking that this PI controller design is perfect, what is to be learned in drives course? We have to learn the modulator, and we have to learn the power converter circuits, how the power converters ultimately convert a DC voltage to a variable voltage, variable frequency output voltage. And you have understood, you have to understand that there are interesting things happening there, because I am not now producing actually a physical sine wave now, though my intention is to produce a sine wave. This voltage intention, I intend to produce it a sine wave, but what we will be producing is instead of a switching waveform, whose effect will be that of a sinusoid, like a sinusoid, which will behave like a sinusoid, which is actually a switching waveform, but many pulsed, many times chopped in a 50 hertz cycle or 60 hertz cycle or whatever fundamental period. It will be many times chopped in order to produce an effective sine wave. Okay, though the shape wise it is not a sine wave. I am again repeating, the shape wise it is not a sine wave, but we will be producing such a waveform which effectively acts like a sine wave to the machine. Okay, so we have to learn this aspect of it, that means power converter, its switching, its harmonics, as well as the modulation scheme. Modulation scheme will tell us how, given V by F, I actually generate the switching pulses. Okay, what time I should turn on, what method has to be there. Okay, so that thing we must understand in the subsequent classes.
Excuse me, sir.
Yeah.
Sir, what if we don't give the feedback in that S omega scene? You have given a feedback. So if I don't give the feedback there,
which one? This one you are talking about, this line?
Yes, sir. Yes, sir.
No, that has to be done, because ultimately the machine's frequency, it is not a feedback, it is an adder. This is a plus thing, it is not a feedback. It is simply adding omega rotor with omega sin, S omega sin. That will be omega sin, right? This is only step. Oh, okay. Yeah, tell me. Yeah.
So what happens if we don't give that? If we don't give that adders?
Very good question. Don't give that. The closed loop control system will then develop directly omega sin. It will bypass. Since you are not helping, it will develop omega sin. Yeah, good question. Yes,
so
it will.
That will also work, no, sir?
That will also work, but you are helping the control system a little bit, because you know it will be slightly above omega rotor. So you are not expecting control system to take care of the entire range, right?
Yes.
You are just shifting the level up, and say that you operate within 20-30 RPM. That is the thing. But yeah, control system wise, it will automatically develop. It is supposed to develop directly the omega sin. Yeah, absolutely.
Hello, sir.
Hello.
Sir, if you don't give like S omega sin, then how will we like we give the omega rotor reference value.
No, omega rotor reference you have given. Omega rotor is less, right? And PI controller will integrate. And and this system stabilizes only if the correct omega sin is obtained. Finally, it has to be obtaining correct omega sin, right? So what it will do? It will integrate for more time, and it will take care of the rotor part also in the equation, in its integration part. It will take more time. If it has started from 0, suppose it has started from 0, this output initially was 0, and it will integrate, and it will first read 400 RPM plus add 13 RPM, 13.6 RPM. But when I know the system has to reach somewhat close to omega rotor speed, I help it by giving it that thing as an additional adder part. Otherwise, the integrator, because the integrator cannot stop until and unless this perfect amount of omega sin is reached, synchronous speed is reached. It cannot stop, because otherwise there will be an error. So this error plus omega rotor, it will be automatically taken care of in the integrator part. Okay. In other cases, I already know that it is close. This actual speed has to be close to omega sin. That's why I directly go to omega rotor and then take the additional part. For example, our supply system is near to 50 Hz, but never close to 50, never exactly at 50 Hz. But the variation is within 2.5%. So in order to make a guess, do I start guessing from 0? I will not start guessing from 0. No, I already know it is close to 50. So I will start putting 50 first, and then say let the controller adjust the difference. It may go 50.56 if the actual frequency is 50.56, or if it is 49.5, then let it go there. So the integrator part, I keep it to the small zone, because I already know that it is close to 50 Hz. Okay, if you don't do that, then the integrator has to work. Integrator has to integrate and reach the, truly speaking, the 50.5 if it has to reach that thing. But it has to integrate to the entire zone. It has to feel that there is an error. It has started from 0. It has 1 Hz, it will be error. 2 Hz, it will be error. 3 Hz, it will be error. Like that, it will continue to integrate and eventually reach. It may take a little more time to stabilize. So those are control system aspects. But from our perspective, PI controller cannot stop till it reaches the correct omega sin, because at correct omega sin only everything is stabilized, everything is balanced, the torque is balanced and speed is balanced. Only at that point these two things attain this thing. So there will be no J d omega by dt term, and J d omega by dt will be 0 only at that point, when it has reached the desired speed and the desired torque, right? So that's what the closed loop system helps us to reach the correct operating point. Externally, only one condition is given, that this speed it should run. That is what the process control tells. But how much load is there in the conveyor belt? It will be implicitly there, and the machine control system will understand it and develop the correct amount of omega sin by adding actual rotor speed with the S omega sin part, or you can directly get omega sin. So I will stop here. If there is any question, you can either write me an email, or I will answer it, or you can ask me in the next class. I hope I am trying to make it clear why we study this and where we have to focus on it. So next classes we will be talking about power converter part and the modulation. This is called a modulator. Modulator's job is giving voltage and omega sin information to it. It will give the pulses for the semiconductor switches. That is what is called modulator. Thank you. Thank you for listening.